Today I'm going to start the lecture with indicating an implication resulting from this distribution of pressure in fluid. Well, since pressure describes the stress in the fluid, so if we displace this fluid and rather than, I mean, if we think about this infinitesimal cube, and if one wall, rather than being another block of a fluid, is another object, then that object will replace the interaction with that other one. So interactions of objects with fluids also result from the stress created in fluids. Well, in principle, actually, it is even more general. If you think about the normal force exerted by the floor on me, it also results from the stress which is created in the floor, and the top surface of that floor is not made from the same material as the floor, but the bottom of my shoe, right? So on one one surface of that infinitesimal plot is part of another object, and that another object therefore takes over the interaction. Well, I noticed that in the lab you are just studying Archimedes' principle, and Archimedes' principle results, in general, buoyant force results from this particular pressure distribution. Because let's think about how actually that pressure is affecting an object which is submerged, and why actually we have a force upward. Why do we have a force upward? Why buoyant force is upward? I mean, just without going into details, because Archimedes already figured out how to evaluate that force. Now, why? But to figure out that there must be a force upward is doesn't require even calculation. Try to find out why there is a force, an upward force on a balloon. Why is it? So what? Yeah, because I mean the answer is that it is less dense than the air, so it floats. By the way, is buoyant force exerted on me or not? Or on us? Yeah. Yes. Yeah, although we have higher density. So buoyant force is actually, well, under certain circumstances, and we have to identify those circumstances now, exerted in a fluid. Whenever object is submerged in a fluid, and the fluid has this particular, is in this particular situation, so something happens in that fluid, there will be buoyant force in it. Now, well, if we take a look at the balloon, which way, you kind of, this is kind of common knowledge and experience, because we saw floating balloons. So we can figure out that that buoyant force actually must be in what direction? Up. It must be up. It is, you know, yeah, because if we look at the balloon, we can identify really, well, one interaction definitely, which is, yeah, let's try to figure out the free body diagram for a balloon, floating balloon. There is a gravitational interaction, so Earth is pulling it down. Well, so obviously something else has to push it up, because otherwise the balloon would fall. Let's try to find other interactions. Obviously there is no normal force, there is no friction force, there's nothing exerts tension force. I mean, you could think about that string which is attached to it. It exerts a tiny friction tension force, but if I include that string as a part of the system, then I would ignore it. Yeah, because center of mass of this entire system, acceleration of the center of mass of this system is determined by the net external force. And so we have to look for other forces. Well, the only other force which we can find out, or any other object which interacts with that, is the atmosphere. And that atmosphere exerts a force upward, and we already know that this is referred as a buoyant force. But why air is exerting that force? And it doesn't matter if the object has higher density or lower density. It happens that if it has higher density than surrounding fluid, it is going to float in the fluid. If it has density less, then it will sink. Well, think about it. How air interacts with the balloon over at that point? It is pushing the balloon to the right, yeah? Because if you think about an infinitesimal block of air on this side, you see that one wall of that block is kept by the skin of the balloon, right? So that skin of the balloon has to push it to the left, so therefore air pushes it to the right. Now how about here? To the left, okay. Which force is stronger, on the right-hand side or on the left-hand side? Why? Because they are on the same height, correct. So pressure at this side is the same as pressure at this side. All right, now think about a surface over here. Well, at the very top. Which way air pushes it? Downward, okay. How come that the balloon doesn't fall? Okay, because on the other side, from the bottom, air is pushing it up. All right, which force is stronger? On the, if I consider the same area, or the surface of the same area, on which surface the force was going to be stronger, and why? The bottom. The bottom will be pushed stronger than the top. Why the bottom is going to be pushed stronger? Because pressure, the lower we go in the fluid, the higher the pressure. Well, now, and where this pressure distribution actually comes from in air? Why there is a pressure difference between high altitude and low altitude? Because of weight, right. So actually, if this was a bubble of air floating somewhere in space, if it were not in the gravitational field of the Earth, so that there would be no gradient of pressure or no distribution of pressure, if it were uniform, buoyant force would not occur at all. So for example, if you make a bubble of water in spacecraft, because, well, if you spill water, it will make a bubble, right? You probably saw it on TV. If you try to put a tiny floating object on that, it will sink, because there were no pressure difference. If there is no pressure difference, then the buoyant force is not exerted. Which actually, now, if you think, I mean, try to do these experiments. Take a helium balloon and let it loose in the car and make a left turn and see what the balloon is going to do. Can you figure out what it is going to do? You think that it will go to the right. No, it won't. It would go to the left, because gradient of pressure now will be that the air will be denser on the right-hand side. It will have higher, it will be compressed on the right-hand side. Pressure on the right-hand side of the car is going to be greater than on the left-hand side. Now, in general, actually, inertial forces are very similar to gravity, because, I mean, it's still not obvious, and I don't blame JD that he came with the conclusion that the balloon would travel to the, will tend to move to the right. If there were no air, this is what the balloon would do, because that inertial force would push it to the right in that non-inertial reference frame. But again, the ratio of densities of the object and the surrounding liquid determines which force is greater, the inertial force, which is proportional to mass of the object, or buoyant force, which is proportional to mass of the displaced fluid. All right, now I will show you that it is proportional to the displaced fluid. All right, so let's now try to figure out the buoyant force exerted on this object. And, well, If it were a cube, so if you don't comprehend this derivation, try with a cube or a block and orient that block actually in a vertical direction. So then it is really easy to figure out that the buoyant force is going to be proportional to the, will be equal to the weight of the displaced fluid by the object. Well, we have already figured out that the force is going upward, and actually, to be more precise, kind of symmetry requires it. So if we have a fragment of surface on this side and fragment of surface on that side, we will see that because the pressures are equal, then they will cancel each other. I mean, that the forces will cancel out. However, in the vertical direction, when the pressure at the bottom is different than pressure at the top, then this is not the case. The two forces don't balance each other. So I can concentrate just on the vertical direction, vertical component of the force. So I'm starting now with a symbol for dBy stands for what? This is the how did you call it?
The buoyant force.
Not the buoyant force. I want you to call it properly. dBy, and this symbol, when it is written in this way, it represents what? Y component of the buoyant force. Correct. It is Y component of the buoyant force. All right. Well, there is a force. It is not buoyant force, by the way. This the force which is exerted by the air on this fragment. Well, it's perpendicular to the surface. Let's say that it makes angle θ1 with the vertical direction, and on top there will be another force exerted on. I mean, I picked up actually a slice. Yeah, these walls are parallel to each other. I mean, opposite parallel, and the other one perpendicular, although it doesn't really matter. All right. So now the vertical component. Well, here I write its area of that bottom surface, differential surface, multiplied by pressure at that height, gives me this force, magnitude of this force. Can you see that? Now, for the vertical component, I have to project it on the vertical direction. So I have to multiply this magnitude by cosine of angle θ1, which is the direction between the force and the vertical direction. So here I have vertical component of the force exerted on that bottom surface. Well, and I put plus in front of it because I recognize that this force is upward. Now this force is downward, so I automatically put a minus sign, indicated that the vertical component is negative, and pressure times the pressure at that location now multiplied by the area gives me the magnitude of this force over here. If I multiply it now by cosine of this angle, I will get vertical component of that force. Well, multiplication is commutative. So in principle, actually, at this moment, I took this product and multiplied by cosine, and I took this product and multiplied by cosine. However, since multiplication is commutative, I can actually multiply this area by cosine and this area by cosine. Well, so actually what I'm going to have, I mean, if I multiply area by cosine, I will really get a cross-sectional area of this object, I mean, of this slice over here. No matter actually what is the angle and what is the area of that surface of the object. Well, now I can use the fact that write it down explicitly, expression. Yeah, I can pull out now, multiplication is distributive over addition, so I can pull out this dA in front, and I have difference in pressure. Well, pressure at one height is density of the fluid multiplied by acceleration due to gravity times the depth in the fluid, and the other one will also have density, acceleration due to gravity, and the other depth. Well, so really, I will have difference in depths. I wrote it here as the difference of depth, which means the distance from here to here. Delta H is the difference between the altitudes of the two surfaces in contact with the surface. Now, if I multiply this height by the cross-sectional area, and particularly if this area is differential, so it is almost a cubicoid, or a block. So what I'm getting here is the volume of that slice. So I can write it down that way. Now I have that the differential buoyant force resulting from the difference in pressure on both sides of this object is equal to density of the fluid, not of the object, density of the fluid, which would be here if we didn't have an object, acceleration due to gravity, and volume of that object. Well, so now if I take entire object, I will have to integrate it over the object, and well, I have already made an assumption that density is uniform. Acceleration due to gravity is uniform. Well, this is true only for small objects. So I can pull out these two quantities and integrate volume of all pieces constituting the object, so it will give me the volume of this entire object. Therefore, in conclusion, if an object is submerged in a fluid, it is subjected to an upward buoyant force. More precisely, it is a force in the direction opposite to the gradient of pressure, which is equal in magnitude to the weight of the displaced fluid. All right. Now, this is actually a very exciting interaction for humanity, because, well, for a long time, actually, and I don't know, it is kind of almost instinctive. I mean, at least I had that instinct, and I was always tempted to fly. And that interaction allowed us, for the first time, to get into the air. It happened in 18th century, at the beginning of 18th century, that we were able to fly using buoyant force. And we still use buoyant force. At the beginning of 20th century, actually, it wasn't even clear what kind of vehicle we are going to use for flying, and until the accident with the airship in 1937, I think, when Zeppelin Graf Hindenburg burned. These types of vehicles were more popular for flights than airplanes. And those vehicles use the advantage of buoyant force. The skin is empty inside, and it contains either helium or, well, nowadays helium, but Hindenburg contained hydrogen, which is lighter than helium. Germans actually wanted to use helium, but they didn't have access to it. The buoyant force, I mean, actually the compartment for passengers is usually very small. I mean, like over here, passengers are sitting over there, and here they are over there in this small console. Well, it is needed because in order to become that the average density, because indeed average density of the object has to be smaller than average density of the fluid for an object to float. Well, therefore, these objects have to have huge volumes. Now, I wanted actually to talk a little bit about physics of balloons because, oops, not that. And I will start with something which is simpler to comprehend, weather balloon. And, well, I want you to think about more than just why it flies, but when it flies, how far it is going to fly, how high it is going to get up there into the atmosphere, and what will happen later on. So let's say that we fill a balloon with helium, and the volume, I mean, it will assume such a volume that you will feel that it wants to fly. How high it is going to fly?
Until the density in the balloon is equivalent to
Okay, until the average density of the balloon together with that load is going to be equal to the density of air. Well, but when the balloon gets higher, I mean, why the density over there is less? Yeah, how come? I mean, why it is less up there? Why the pressure up there is less? Oh, yeah, in other words, why pressure over here is higher than up there? Because of gravity. Yeah, what does gravity do to air, really? Well, not only that it pulls down, it does more than that. I mean, gravity together with the air above, it does something to air below. It squeezes it, right? Well, so when it squeezes it, it is under strain. Yeah, the volume is being compressed. So in the same volume, we have fewer molecules up there than over here, because over the lower we go, the more it is compressed. Well, so if this was made from a mylar foil, for example, or aluminum foil, then I see what would happen with the balloon. It would simply float up there until it gets to a particular height, and when the buoyant force will be equal to the gravitational force, it will stop it will stop rising. It will stop. It will stay at this particular level. Well, but weather balloons, I mean, it's not actually a coincidence that it's made from a rubber, from a rubber foil. It's an elastic. So what happens with the balloon as it goes higher? It expands, right? It is going to become larger and larger and larger. At the same time as the pressure, as long as the pressure outside is going to be smaller, the pressure gas inside will push on the walls stronger and stronger, and eventually eventually what this balloon is going to do? Pop, right? I mean, and all in the balloons which you release, I mean, these toy balloons which are filled with, most of them will also pop. Otherwise, we will have, by now, we will have a lot of those tiny children balloons floating in our atmosphere. They don't, because as they get high enough, they break and fall. Well, actually, probably you see, I mean, very often these types of balloons are equipped with a parachute to recover the recording instrumentation. All right, so they will pop at a particular height where the pressure, where the outside pressure is sufficiently low that that the balloon is going to expand to such a size that it will exceed the rupture property of that foil. Now we also have balloons. Oh, take a look at these balloons. These are high altitude balloons, and actually it's launching of the balloon. it is not made from the foil is not elastic, but look how it is filled up. What can you see over here? It's not full. Well, it's not full at the ground. Yeah, because now it is going to get higher and higher and higher. Yeah, so what is that? What is the pressure of the gas inside right now? I mean, if you look at that. The same as outside, correct. Yeah. Well, all the time it is going to be that way until it gets really very high. And actually it gets almost, I mean, it gets already to the point that as you can see the, well, you can see space over there. How come? I mean, how do I see that it looks at space, not at air? Because it's black, right? Sky outside is black. Yeah, only on Earth, because we have that atmosphere and which interacts with the light in a particular way that it produces this blue impression. When we get high, it becomes black. All right, now how about this one? This one is also a very, very interesting device because, well, over here, pressure inside is higher than, well, no, it isn't. Yes, it is higher because it is the foil actually holds the gas inside. Now, in a hot air balloon, it is that the pressure inside is all the time the same as pressure outside. Yeah, how do I know that? Because there is a hole over here. Yeah, there is a hole over here. I mean, I know that very often people have a misconception that, well, when we heat it up, pressure inside increases. Well, pressure will increase if we contain the gas and heat it up. But if we have an opening, then it is going to flow away. The same way, actually, the same thing happens with lungs. Yeah, when we breathe, no matter if I'm inhaling or exhaling, pressure in the lungs is all the time equal to the pressure outside. It is that when I expand my lungs, immediately I feel, I mean, if there is an infinitesimal differential in pressure outside and inside, it is filled up with the pressure, with the region of higher pressure. So when we breathe, all the time pressure inside the lungs is the same as outside. All right, now I want to talk about another type of interaction. How about I will show first this, well, no, maybe not. This type of interaction, in principle, is a very ideal description, and I even don't believe that it happens. But in a limiting case, you can think that it is a good approximation. And because in physics everything is approximated, then we can use these approximations. So this type of interaction, which actually leads to a force which we recognize as lift, yeah, because aeroplanes don't use buoyancy; they use lift. And I will be talking now. I'm talking now about this: how lift is created and how it is described. Well, I want to describe, derive an expression which describes this type of interaction in kind of an ideal environment. So this ideal environment requires that the fluid is ideal, and ideal fluid requires that there is no internal friction. So fluid is non-viscous. We say that it is non-viscous. That flows steadily. It means that if I consider if I consider a point, let's say this point of space, it means that all particles passing through this point will always have the same velocity. This means that it flows steadily, that it is incompressible, so the density does not change. Bulk modulus is infinite in principle. You can say that. So no matter what is the pressure, it has the same volume, and it does not produce vortices. This is a description of an ideal fluid. And, well, if you think about water in a pipe, you can consider water in a pipe as an ideal fluid. Actually, also air, if it flows at not too fast in a pipe, it will be an ideal fluid. And even without, even outside, it could be approximated as an ideal fluid. So when the rate of flow is small, and it is the rate has to be, I mean, small. What does it mean, small? Because some speed with which wind actually blows outside of an aeroplane is still considered slow. Aeroplanes really fly slowly in air. The important thing is that the flow is we call it laminar. So there is no turbulence in the fluid. It's smoothly, particles smoothly move along the surface of the object. All right. Well, if something like this happens, if we have this type of a fluid, then work energy theorem actually leads to an equation which relates various quantities in that fluid, in particular distribution of pressure. And, well, so let's say that I have a pipe through which water flows, and water is, in a pipe is pretty well close to an ideal fluid. So let's see that we have water here. Well, now think about that this pipe has various diameters, and it goes at through various heights. Yes, so this pipe is higher than this one, and this pipe has smaller diameter than this one. Well, but water flows through that. Now, let's consider just this system of particles between these two surfaces. I imagine one surface over here and one surface over there. And as time passes by, this system is going to move a little bit forward. But I will think only about this particular system of particles. So for me, water between this surface and this surface is considered my system. Now, the water in front is an external system to my system. However, it interacts with my system. And the water behind that surface also doesn't belong to my considered system, but it interacts with that. And it performs work. And only actually this, I mean, this water and Earth are performing work on it. Now, Earth is a conservative, I mean, gravitational interaction is conservative interaction, so I will use the work energy theorem in which I will compare change in mechanical energy with non-conservative work. So what performs non-conservative work on my system now? External work, right? But what? Yeah, I identified three objects. Earth is performing work, water in front, and water behind. Which one is any of those performing conservative work? Earth, correct. So non-conservative is only done by water in front and behind. All right, so let's now consider time dt, and what will happen with my system. It will move forward a little bit, right? So this surface will move to that point, and this surface will move to that point. Now, which one will move further? The bottom one. Why? Because well, the diameter is smaller, and if if I consider an incompressible fluid, it means that this volume over here must be equal to that volume over there, right? The two volumes have to be equal. All right. So let's say that it times dt. This one moved by distance dx1, and this one moved by distance dx2 to the right. So from the work energy theorem, now over here I wrote an expression for mechanical energy. Let's take a look what is here. Well, I see that well, if I look at this system, well, previously I didn't have those particles, so these particles over here give me a gain to the total mechanical energy of the system. Can you see that? Now these particles over here are missing now. So this is what I lost in kinetic energy. Now the particles between this initial surface over here and that that final surface over here, well, they were replaced, but in an ideal fluid, all of them will move like the previous ones. So the total mechanical energy of the particles over here didn't change, although they were replaced. Do you understand me? Yes, so if I think about total energy, I recognize that in this volume I have no change in mechanical energy because the replaced particles behave exactly the same way as the particles, the original particles. Now some of the particles from this volume moved over here. So this is a gain in mechanical energy for my system, and now particles are missing there, so this is loss. So in the result, I'm writing now here an expression for, well, gain in kinetic energy. So cross-sectional area times this distance gives me the volume of those particles. This is volume of those particles. I multiply it by density of the fluid over here. So this gives me mass of that fluid over there. I wrote an expression for the speed over here, so, and divide by 2. So this is kinetic energy of those particles over there. Can you see that? Now, over here again, this is volume. If I multiply by density, this gives me mass of that water here. If I multiply by acceleration due to gravity, I'm going to get mg, right? So this is mg, and y is really elevation, yes, so it is height, mgh. So here I have gravitational potential energy of the particles which added mechanical energy to my system. Now those who lost, so they don't belong anymore to my system. I did it again. I recognize that this is volume of that liquid. This is mass of that liquid which is now missing. So this is kinetic energy which disappeared from my system. And this is potential energy which disappeared from my system. All right, so I wrote an expression for change in mechanical energy of the system. Well, the change in mechanical energy is supposed to be equal to the non-conservative work. Now, who was performing work? Fluid in front and fluid behind. Now, fluid in front was performing positive work or negative work on my system? Negative. Why? Because it was pushing the liquid, I mean my system, backwards, while the surface was moving forward. So it performed over here, this fluid performed negative work on this fluid. On the other side, the fluid behind pushed it forward, so it performed positive work. And I can find out that work. Yes, so it is pressure times area gives me the force exerted on the system times displacement. So this is work performed at this surface. Now this is work performed on the other side. And now I can recognize that this volume is equal to this volume, which means that A2 times dx2 is equal to A1 times dx1. And everywhere I have a product A and dx. All of them, therefore, are going to cancel. And therefore, after simplification, I'm getting an expression which says that for an ideal fluid, the sum of the pressure, the kinetic energy, and per unit volume, and the potential energy per unit volume remain the same. So let's say that if I had a pipe which is narrow and one spot and wide on the other side. Yeah, so imagine a pipe, let's say horizontal pipe, narrow here, and then it gets wider. Where pressure is going to be higher if fluid flows through this? Yeah, in the narrow one, it will have to move faster. Do you see that? And in that wide, it will move slower. Where the pressure is going to be higher? According to this equation. It is counterintuitive because I know that we often associate pressure with that speed. And it's an error. If you look at this expression, so now height is the same. Yeah, so we will have this expression and this expression will cancel. Now we can see that the sum of kinetic energy and pressure in the narrow pipe and in the wide pipe is going to be the same. So if fluid moves fast, it has high kinetic energy, therefore pressure has to be lower. So in a narrow pipe, pressure is smaller than in a wide pipe. And whenever fluid actually moves fast, then pressure becomes smaller. And I have a demonstration for that here. I think that after demonstration I'll finish the lecture. So this blower will blow now air straight up. So here I will have a column of moving air. Over here I have still air, right? So, well, according to this equation, in that column over here, pressure should be lower than outside. So if I put a ball over here, what should happen to the ball? It should go toward lower pressure. I mean, some of you probably, it's possible that you saw it because I saw it sometimes in a shopping center, this trick. Now you see that it really stays in that low pressure. It is always pulled towards that column of moving air. Now take a look at this. All right. This will be all for today. Thank you. See you tomorrow.